All right, welcome. MAP4C, day 45 yesterday, or last day we were talking about linear models. Today we're talking about quadratic models. And the goal today is both review and today's actual goal to describe trends in graphs and recognize quadratic models. Describe the trend shown in the graph. All they want us to do here is sort of just like tell the story that the graph is telling. So we always read it as the independent variable is increasing. So as burger price increases, we always read that from left to right. Well, what happens to the daily revenue in hundreds of dollars? Well, it increases quickly at first and then more slowly, comes to a stop, right? That's the maximum, right? Maximum, and then it decreases slowly at first and then more quickly. So that's quite a few little things to put in there, but we can do it. Revenue, I'm going to put revenue increases quickly and then more slowly. And I'm going to put the maximum in brackets until a maximum revenue of, and I'm going to read that point where we go, I don't know, maybe 650 bucks, because it's in hundreds of dollars, $650 per day, um, when the price is $4 a burger. Then the revenue decreases slowly and then more quickly, right? Starts decreasing. Good. Maybe that's more detailed than we need. That's certainly a level 4 type answer. Why does it make sense that the model would be quadratic? And the idea here is, when the burger price is low, even though lots of people would be interested in buying a $1 burger, they're only $1, right? And so there's not a lot of money coming in. Similarly, over here, yeah, if burgers are $7 or $8 a piece, that's a lot of money coming in, but you're not going to sell many because people aren't going to buy them, right? And that's my answer. As burger price increased at the start, people would be buying them, but eventually people would stop buying them because they're too expensive, right? And so where's the happy medium? Well, that's at the maximum of $4. That's it for that one. That's kind of review. And then we also want you to read page 266 and carefully do number 2. Um, Probably on another piece of paper. I don't think there's enough room on this page, but I am going to take that up shortly, so please try that. Pause the video and try that question on page 266. I'm going to take it up right now. Determine the coordinates of the vertex. Remember, the vertex is the maximum or minimum. Both of these are maximums. And I just have to read the x-coordinate and the y-coordinate. Notice 150 is easy to read, but this is kind of weird to read. 2 squares is worth 5,000, so 1 square is worth 2,500, right? So if I want to go and figure out what the revenue was, there's 20,000. Each square is worth 2,500, then this would be 20,000, and then 2,500, 22,500 altogether. The height of the ball over here, the maximum is when the time is 2, and the maximum height is each square is worth 2, it looks like, so 2 more than 20, 22. And I should write sentences for that, and I have. Hopefully you did too. Ticket revenue was a maximum of 22,500 when they sold 150 tickets. The ball reached a maximum height of 22 meters after 2 seconds. This is the story that these quadratic functions are telling. I think that's it for the 3-minute review. 3-minute review is a 5-minute review, but that's okay. Oh, there's an activity here. So there's two ways you can sort of play this. You can skip the next couple of seconds until I get onto the lesson, and you should be able to handle the lesson without doing the activity, or you could do the activity and come back to the lesson. So either, skip this and do the do note, or stop this entirely, wait, do the activity, and then come back to the note. So tomorrow would be a double lesson for you. If you want to do it that way, I suppose you could. Come back to video later. Okay, and I am going to sort of show you what you're supposed to get out of that activity right here in a second. So if you're going to do the activity after the lesson, then you'll want to fast forward this a bit because it won't make much sense without doing the activity. So in class, I'll give you a sheet of paper, and then you sort of fill this in with what means to be a quadratic or not quadratic from the graph. Well, the graph is a parabola shape. Right? For not quadratic, it's not a parabola shape. What makes the table of a quadratic relationship a quadratic relationship? Well, it isn't the first differences are constant, it's the second differences are constant. Right? If the second differences are constant, you've got a quadratic model, quadratic relationship. And then if it's not that, it could be something else. This one's linear. This one is, well, we just don't know what that one is. It's not quadratic, though, because the second differences have to be constant. For a non-quadratic, the second differences are not constant. What about the equation? What do equations look like? Well, the quadratic, the parabola-shaped equations have a squared in it. One of the variables is squared. This one's t squared. This one's x squared. So in the formula, we have a squared for quadratic. For non-quadratic, we don't have a little square here. This one's linear, and this one, if you remember back to grade 11, is an exponential model, and we'll actually talk about exponential models tomorrow. Hopefully you got something similar to that out of the activity. Now on to the examples. So out of that activity, what we were supposed to get: the summary of the 3-minute review and the activity or the exercise. Quadratic models have their graph is a parabola. Graph is a parabola. The second thing that we should remember is the table. They have the second differences constant. Remember what I mean by differences is difference between y values, as long as the x values go up by the same amount. Second difference is constant. The equations have a squared in them. Now the general form looks like this. And he did a bunch of work in grade 10 and grade 11 sort of talking about these values of a and b, but essentially if the a value, if the value in front of the x is positive, then you're going to get a parabola that opens up. If the a value is negative, it's a smile, or it's a frown rather. Negative. That kind of makes sense. Positive people are smiling all the time. Negative people are frowning all the time, like Mr. Rexall, always frowning. My a value must be negative, I guess. Okay, I'm going to pause, come back for part 2, okay, and actually get into the examples here. I don't think there's anything else on this slide. I'm going to stop it there, and we'll get back into part 2 with the examples.